As before, please do interrupt to make this a conversation with each better. So what did we see in the previous lecture was that, topology is all about wave functions, and it's very kind of irrelevant to think about the energies when it comes to topological properties of the system. So we can think about the projector instead of thinking about the Hamiltonian. Okay, so projector into a band that I called alpha, which is just the sum of the block states over that. And of course, we can change the bases, and we can go to the Vanier basis, and then we are summing over Vanier states in real space, indexed by I. And we focused very little on this because before we only talked about atomic limits, and atomic limits, we know that if we do things properly and do things smartly, you can actually squeeze all of these guys into delta function like states, and I wrote them as these phi's, which have the property that they're basically perfectly localized, delta function localized on a site of the lattice Q phi alpha, and they have some orbital character, which would be dictated by the irreducible representation of the point group. So this would be the local orbital. So in atomic bands, we have this nice feature that everything is represented locally. Everything can be described in terms of the spaces states. And in particular, all of the symmetries of the space group, they can be represented as some local representation in these states. But this is not everything. In order to know how these states look like, we also need an additional information, which there is some topological aspect to it, which is the position operator. And we know that the position operator, when it's projected into the band, let's say the direction I, will be some expectation value of the xi, which is the very Zach phase times plus some lattice vector, again. Okay, so that would be kind of like generally, that would be all of the topological quantities of an atomic band. And we talked about topological obstructions in this sense as two different atomic limits that cannot be adiabatically connected one to another. Right, so that is the notion of topological obstruction. Just means that some two spaces cannot, and we're using a bit freely this symbol, usually means that not isotropic, but just means there's no unitary matrix that would connect the space of this projector to the space of this projector. And we defined an operator, the basis independent version of the overlap matrix introduced, well, generally used, but in construction theory, but also talked in a topological context in the work of Vanderbilt, which is the overlap operator between bands alpha and beta, which I wrote as alpha, beta equals gender to beta, and that's transposed. And what we know is that if these two spaces are not the same, then the rank of S is smaller than the rank of each one individually. Okay. So this is a singular operator. It has determinant 0 in a suitable valence. So what we also said, okay, so this of course happens when this projection is 0, when there's like a basically the projection is not perfect. You could eventually think about enlarging this operator to something that you would put here a symmetric unitary matrix, and if this always has a 0 determinant, then this is an actual one-to-one correspondence rather than just one in one direction. So then we said that when you have different things that are debatically disconnected, sometimes, almost the times, you have different boundary signatures. And we looked at the concept of filling anomaly. Which basically meant that we could not represent anymore our symmetries in a local fashion with open boundary conditions. So we looked at the SSH chain, which basically protected by inversion. And let's imagine that this is the SSH chain, and if I have state fields on exactly the invariant line, and when I open that chain to have open boundaries, I will have to split one of the positions by two sites. So the multiplicity of this site, which was 1, so inversion symmetry would take it to itself, becomes something that has multiplicity 2. So if I have that site filled, I will need to somehow spread my electron through these two parts, and I cannot do it. So what would happen in terms of the spectrum is that I would have some in-gap states which are degenerates, and I can then fill one of them. And by filling it, I could, when I were to choose where to fill my electron, I'm breaking weakly the symmetry that protected the SSH chain, which was the inversion symmetry in this case, and I would put my electron on one side, and that would lead to a total polarization that is quantized. And it would match the quantization of the bulk polarization as well. And we talked about the quadrupole insulator, which was a bit of a more weird beast. And in the quadrupole insulator, where you have two field orbitals and they have the constraint that it mirrors and commutes, we have two field states, and then we have the possibility of having, with open boundary conditions, those two field states being shared by 4 corners. So you do have a filling anomaly as well. But this type of anomaly is a bit more weird, because if I were to put periodic boundaries, and let me just do it here pictorially, it's something that I didn't do the other time. So these two are the same. So now, if these two, basically, I could, if I identify these two guys, I have one field state here, in the middle. I put it here, and now I could easily move it to the center, and there's actually no quantization of where this charge is when we have any kind of periodic boundaries. So that means that basically what I have here is a boundary obstruction. Meaning that the two, the diabatic discontinuity only exists if I have open boundary conditions. I can write it basically, I'll just leave it like that. Okay, so now let's talk about topological bands, and you've heard a lot about this already in this school, and you've heard a lot about interactions and how they come about. So let's just ask ourselves, maybe, like go a little bit more basic and ask ourselves why indeed we would expect states in matter in a crystalline lattice to have this kind of local description. It's obviously we don't need that, right? And we can simply write a very, very simple Hamiltonian, which everybody has looked at. Which is basically half of the SSH model that has a Chern number, insulator. And how can we interpret this? You can interpret this, for example, in a square lattice, having s orbitals, and that would be sigma z. The s orbital is plus s, and some p orbitals on top of it. P orbital is odd, right? What this m does, they just put the energy difference between them. What this t does makes you hop in the lattice, right? And what this lambda here does, it couples s's and p's with some antisymmetric coupling. So one thing that you can convince yourself very easily is by looking at ky equals 0 and ky equals pi. Just put ky equals 0 and ky equals pi in this Hamiltonian, and then so like reduce it, and you very much get the SSH Hamiltonian that we had before. So this lattice has mirror in this direction and mirror in this direction. So it's fixing ourselves to ky equals 0, ky equals pi. I basically recovered the SSH model. And I can choose a combination of parameters of m, t, and lambda, and do that as an exercise, where basically the ky equals 0 would be an SSH model with x equals 0, and ky equals pi SSH with x equals pi, equals 1/2. Right. So there's some range of parameters that this would happen. Okay. So if I'm going to plot here the expectation value of the position with respect to k, 0, right? I would have 0 at 0, and at pi I would have 1/2. So somehow the states which are all with ky equals 0 are located in a different lattice position than unit cell position than the ones at ky equals pi, and of course do some interpolation, because we do not really know what would happen for the different QIs, but that needs to be continued. So we do some kind of interpolation. What does this mean is that we're basically seeing the position being coupled to the momentum, the position in one direction being coupled to the momentum in the other one. And you know this. You've seen this before. And you've seen this before in the lambda level problem. So let me. So what this here is, if I have the Brillouin zone, what I'm doing, I'm computing what is called the Wilson loop spectrum. And I'm taking all of these states, so this is now the 2D Brillouin zone. And I'm taking all of these states and I'm calculating what is the expectation value of x in the other direction. I know that this will be, if I keep my mirror symmetry, I know this will be quantized. So you only have one state field. This guy better be either on the center or the edge of the unit cell. So that's going to be the trivial SSH chain. but I do have another line in the Brillouin zone, which is inversion symmetric, which is kz equals pi, and that may as well be in a different position. And in that case, if we tune the parameters correctly, it will be. So as I take different lines of this of the Brillouin zone, and I calculate the position for every single one of these lines, which is labeled by K1, what I'm doing is calculating the Wilson loop spectrum, and I will find this flow that will tell you like each momentum will giving me a position, and it will wrap around the unit cell. So basically, if I am looking here, basically Ky is going to be somewhat proportional to X. So I would look at some hybrid value. So I would look at these states localized in one of the direction, of course, extended in the other. They will be here at K equals 0. And as I would move on, they would just keep on going. Right? And that's exactly what we expect in the Landau gauge, in the Landau problem. So our assumption that basically looking at the position would be everything we needed in order to describe the states. Okay, we have a problem now because it's really not well defined, because which one is it? So if it goes from one side of the unit cell to the other side of the unit cell, the position is really not well defined. I would not know really how to choose this.
Sorry.
Yeah.
So I'm pretty confused on the left node figure. You have two axes go K1.
Oh, I am using a mistake. So this needs to be Ky. So this needs to be Ky, needs to be Kx, because here I wrote X. So at the specific Ky, I need to be able to find the position in the X direction. So if we go back to let's put here, if we remember that we did symmetry indicators for the SSH chain, and we associated this position with the product of the inversion eigenvalues or the reflection eigenvalues. In this case, which was the position 1A, we had plus at K, in this case at Kx equals 0 and Kx equals pi. And when we had 1/2, we were associated that with the position 1B, where we had plus minus at Kx equals 0 and Kx equals pi. So if we're now plot that in the 2D Brillouin zone, basically we chose that Ky equals 0, this line, to be an SSH chain, which is trivial, so it's basically plus. In the Ky equals pi, we had plus minus. And this is basically, so here, what the momentum position is 0, 0, 0 pi, pi, and pi 0. So now there's something very interesting about this, is the total parity here is minus instead of being plus. And one thing that you can do is just to see, would there be any atomic limits that would be represented in this way? And you can just very quickly convince yourself that not, because you can try making it forcefully. Okay, so imagine that I have a unit cell here, and I have an s orbital right in the center. So basically it's even under, it's even under inversion, and it doesn't really matter, like we did with the SSH chain, right? It doesn't really matter which position in the Brillouin zone is always, in these high symmetry points is going to be always plus. So this case is always plus. If I have it on one of the sides, and what I'm going to do is, by inverting, I'm going to take it to this position. It means that I need to translate it back in order to get there. That I'm going to have e to the I kx added to my representation of inversion symmetry. So that would swap these two signs, right? So I have plus, minus, and you can continue doing that. But every time you swap two signs. So the total parity is always going to be fixed. And that is actually the entire idea of Cohen-Kane. Which is basically the parity index, right? The parity priority criteria. So if you look at this and if parity gives you minus, you know if you have something topological. So basically our assumption that if we were to do the right transformations within the space of the block states to construct very, very localized value functions, and I could go all the way from having my value functions completely localized, it's not true anymore. It must be not true because I really don't have any way to justify that with any local basis. So where could that go wrong? Where could that go wrong? Well, Vanier functions have this form. Someplace. This guy is a periodic function. So the only way that I cannot localize this guy is just in terms of properties of Fourier transforms, is that there's something going wrong in this part of your function. So actually this guy cannot possibly be smooth and periodic. So there are some irremovable singularities in the definition of your wave functions in the Brillouin. In fact, there's some that's so then the expectation value of the position operator that we had before is not really well defined. It is not really something that I can talk about by states. So the next natural thing to go and look at is what? If we cannot, like, if this is not quantized, this is not a quantum number. This will not give you quantum numbers of your state at all. So the natural thing to look at is basically the next moment, right? So position is not well defined. It means that when you project the position operator into the vents, it becomes fat to some extent, and that is basically the fatness that we are going to need to characterize. In terms of projectors, if I write this thing, I can write it in the following way. Which is, if I just combine this, I have I1 minus alpha. This is basically the projector into the other vents. So if my states in P are going to be eigenstates of the position operator, this is going to be trivially zero, right? Because this will commute with the position operator. P times P1 minus P is just going to be zero. So everything that will deviate from that, when alpha, this is a quantity that is called the geometric tensor. That is really going to quantify how far you are from this limit of being an eigenstate of the position operator. And I think that there was already a lot of talk about this operator, and a lot of, yeah, I think Andre probably talked about this part as well. So this operator has a real and has an imaginary part, or has a symmetric and an anti-symmetric part. So you can basically write it. And I'm not going to dwell too much about it, because exactly I think that Andrea already went on about this. So I'm sorry if my notation is different. So some people write the full geometric wave tensor with a G, and then the small g as the real part of the geometric tensor. But let me put it this way, where I basically divided the geometric tensor that I call T in a real part and symmetric parts, which I call G, which is called the quantum metric, and an antisymmetric part here, which is the Berry curvature. Okay, and I can take, of course, I can take matrix elements of this in momentum or in position, and those will be then recover the formulas that you might know about it. So it's actually quite nice to think a little bit about what this Fij, this antisymmetric part means. So if this is just the position squared, the variance of the position operator, the Fij is going to be written as the commutator, right? Because you basically are taking the antisymmetric part of this. And as the commutator of the position in X and in Y. So an I and a J here, of course, I and J indicate different directions. So what does this mean if you take elements in momentum space? You look at the Brillouin zone. The position in momentum space is basically a little step, right? It's derivative in real space. So what you're doing here, you're looking at how the states evolve as you go in a little loop in the Brillouin zone. I think that is a nice way of imagining them. So if you're, so this is what's doing with the commutator. You go first a little bit in X, then you go a little bit in Y, then you go a little bit back X and Y with a minus sign. So you might pick up a flux. That is your Berry flux. That's not what you're going to pick up. And that's going to tell you something about the natural geometry of the space of the band. And if I take the trace of Fij, which is basically going to be just a commutator of the expectation value of X and J, what you're going to pick up is the Chern number. So if you're going to integrate over the entire Brillouin zone, and you're going to pop out the number that it's going to be used topological invariant. And it's quantized. So you see that you can get the quantized quantum number out of position operator, but it's not on the first moment, it's going to be on the second moment. So that is quite interesting. Many times you don't have a Chern number to talk about, but you still have much of these properties. And there's some relationship. This is a very, this is from the same operator. So there's a constraint between how you relate the real part and the imaginary part of this. So when you do have a Chern number, it actually puts some constraints on this part here with this real part, which is the quantum metric, that will tell you. Yeah, sure.
So what is I and J? You mean the dimension?
So I and J are the directions, so X and Y. So this part
2D Fxy is only right, right?
Right. So then this is a 4x4 matrix. Right here you have the XX, UIY, FXY, FXY.
My question is why the trace of fxij should be c? Because you essentially check number is the integral of the fxy,
Yes,
right?
right.
When you say trace isn't it under?
Okay, so sorry, they should have said that. When I take the trace here, I take the trace over position. So this guy, this projector is very, very big. These are still very big operators, okay? So I take matrix elements in K, then I could take the trace here would be integral over K. I could have, might as well just look at position, at the elements in position space, and then I'm taking the trace over that. Okay, so I'm just expanding it some basis. So yeah, so this is maybe a little bit too fast, but that's exactly what it is. So in this trace, I'm including the integration over the entire momentum space. Yes.
Good question. So when we said that the first moment is not a good quantum number, is it related to the fact maybe it's not gauging variance? Maybe you need to go to the second moment because only the second moment would be gauging variance.
Well, in a sense, it is not gauging variance. Well, no, let me put it. You can define the expectation value of this operator, and I think that will still be gauging variance. But it's still the thing is that it's momentum dependent, right? So the position, it goes a bit against being a single position because the position in X will not commute with the position in Y. If you measure X first, then you if you measure Y first, and then or Y second, and you measure Y first, it's all going to give you different numbers, right? So it's not in a sense that I can equally define the position in X and Y. So in that sense, it's not really well defined. I mean, if you choose a specific K, you'll be able to write this at the specific KY. Let's say X, just X, and you have a number that is well defined, but you will have the problem that it will really depend on KY to the point that you could not even do any unitary transformation on your space to get the perfectly localized state. It's pinned to be response. Okay, so yeah, so I wanted to say something else about the real part of this operator. And I wanted to say something, yeah, so that the trace of Gi, J or II, because in this case it's going to be diagonal, it's going to be a number. And this number is something that quantifies how fat these your states are. Okay. So that's the spread of the value function. Okay, so then what do we say about adiabatically discontinuity between two different things is that the determinant of this S matrix, it's going to be 0 between a band A and B. And now what I'm going to say is that if I choose A to be a topological band, and if I choose B to be an atomic band, this is always going to be 0. Right? There's really always a 0, a singular overlap between any topological band and any triple band.
The topologically mean in a very broad sense.
I mean, in the sense that I cannot consistently find a position. So that there's no, or that there's a value of.
So what I'm saying, it includes a fragile topological.
It includes the fragile topological as well. So if I do not have an adiabatic path to something localized, if I have a value obstruction, then I know that this is going to be singular for any constant. That's just by definition. But this is another way of you seeing how does the value obstruction come about. Because imagine that I try, right? Imagine that I actually try. So I try to construct some states I'm going to call epsilon, which are going to be localized by definition by projecting some set of localized, perfectly localized, delta function localized states into my band. These guys are exponentially localized. There's no way around it. Okay? So this guy is local. This guy is topological. And this guy is local. Then I'm going to get something, but the overlap between these states, between different states at different positions, it's going to be exactly the overlap matrix in the real space basis, so in the I like there. And I know that this has a determinant 0. So if I were to go now orthogonalize my states, so I constructed these states, but they are not orthogonal necessarily. I just constructed a set of states. So if I were now going to try to orthogonalize them, which I can do by constructing new states, I would have to basically invert this matrix, this overlap matrix. And when, of course, I know that there's a determinant 0 here. If I have 1 0 eigenvalue of this guy, I won't be able to do it, but you can also read it in this way. It's going to, you're going to start coupling to longer and longer and longer further away states. Right? This is the way to interpret this. So if you're going to try to orthogonalize them, but the fact that you have very small eigenvalues in this matrix, it means that you're going to have to start modifying other localized states very, very far away. And you were actually not, when you try really to do that, you eventually find out that these states start getting longer tails, all the way to have actually polynomially localized states, becoming polynomially localized states. So eventually, in the limit that you do this over and over and over again, these states are no longer going to be exponentially localized. That's what people try to do. So it's really a property of a property that you really cannot. You will always have a singular overlap with any local basis that is symmetric that you cannot possibly construct exponentially localized by the states. So those are all kind of the same concepts. Yeah.
Because modeling that behavior, so then project the topological then.
Oh, sorry. So yeah, should put here. So the topological, we project in the topological. I tried to say alpha is by topological. Yeah, thank you for trying to keep this somehow organized. So these states, which are localized states, they need to have both index alpha and beta. This is the projector into the topological band, and this is a set of states that I chose that are perfectly localized on that are labeled by beta.
Okay. So my question is: so do you assume gamma to be local, or do you know that gamma has to be local?
It has to be local because it's the projection of a local function into the band. This is a delta function, and when you project it, it will be exponentially localized. So by this, what I mean is that you can definitely construct exponentially localized functions projected into the band. They're not going to be necessarily orthogonal to each other. And if you try to make them orthogonal, then you're going to start growing for the polynomial. So there's kind of like interesting consequences on this. Which I think they're, in spirit, nice to talk about and to appreciate, and which, if we were able, right? What about these states? These projected states. Really, they always need to be larger than the unit cell. Right? They need to come to be fatter than the unit cell, because if they weren't, then you would have one per unit cell. They're completely, they would be orthogonal because they don't have any overlap. And boom, you have a basis that spans this space. So this is larger than unit cell. So there should be really a minimum of the spread of these states. If you eventually come, it makes sense that there's a minimum of spread of this local states in the band. It's not necessarily easy to prove in general. It's possible in the chart case, there's a trace inequality that you can use, but in general, it's not necessarily the case. But it's immediate that it must be larger than the unit cell, just because of orthogonalization. And another interesting aspect is that there's always, if I do such a projection into these localized states, there is always at least one which is invisible to this projection. And there's a state that it's invisible. So it means that if you perturb your state by something local, there's at least one state that doesn't see it. That's kind of nice, because it's it needs the number of states on in the projected space. The number of independent states are going to be less than the original. So this is really, I think what is the most important thing about topological bands, and where all of the interesting things then afterwards come, and we have heard so much about it, which is this funny obstruction. Okay, so then what are interesting things, physical observables that come with it? We can start and look again at our filling anomaly, because I think that gives you a little bit of a good intuition of how things come about. So if I have, let's imagine like boundary states in the model that we talked about before. Now we have Ky as a good quantum number. And we know very well how to look at Ky equals 0 and Ky equals pi. And I know I have a filling anomaly only at Ky equals pi. So only at Ky equals pi I have in gap states. And at Ky equals 0 I have none. Right? So if I'm filling one of these, here I don't have anything. So for other Ky's, I somehow need to connect these states somewhere. And it will connect to the valence band into the conduction band. So in filling anomalies, there's nothing really anomalous about it, in the sense that nothing can leave, it's not required to live on its own or as the boundary of something. But here it's actually much more interesting, because it gives rise to a state that could only be the edge mode of a two-dimensional system, right? And that's an anomalous, really the anomalous boundary state. And you wouldn't even have, basically wouldn't even have enough states to make it completely living in 1D, because if you get one of the K's, at least is absent. So if we look at any topological phase transition where it involves a gap closing transition, right, where we have on one side we have certain states, on the other side we don't have certain states, we know that we need to close with both gap, and that closes in a Dirac point. That usually closes as a Dirac point. And a Dirac point, the wave functions change very fast. The wave functions very, very, very quickly when you're very close to the Dirac point. So if you are going to plot, which you now have a quantity, which is this trace of the real part of the geometric tensor, which really quantifies how fat things are, you're going to see that on the trivial side, you could go all the way to 0, right? Because you can make it infinitely sharp. On the other side, you have some minimum, which is guaranteed by the Vannier obstruction. What is happening in the middle is that your wave function needs to become very extended, and it will actually diverge the real part of the geometric tensor. And if you're going to compute it, you're going to find out which is direct. It will always happen for any Dirac one. So you will always have a divergence of the real part of the geometric tensor for Dirac ones. So we talked about something that was a shared insulator that had a Chern number, but really it doesn't. Yeah.
Is this also true that it's not divergent of any gap closing? Because typically when you have the quantum metric, it comes with it as something 1 over energy. So when you close the energy, being a drag point or anything else, it's always divergence at the gap.
It's really about the wave function, right? So you will have this quantity is going to be something like so it's going to be something like this, the second derivative of the wave of sine, right? So this is something. I'm not going to write something down here. There's a mistake. And so it really has to do with the derivative of the block states. So if you just trivially close to get to bands to touch, this is not necessarily going to give you some divergence in the quantum metric, because you're just basically touching to, you can completely find a smooth gauge that goes all the way through. In a Dirac point, you really cannot do that. There's a singularity there. So as you go closer to the wavepoints, you're going to be becoming faster. So that's so it's not just the gap. It's just not the gap closing that will lead to this. It's really a Dirac gap closing. But you could have other types of band touchings that would be singular, and then there you should expect as well some divergence from metric or squared. Okay, so really, this idea of I think there's a point to make here, which is this idea of topological band in Vannier obstruction is really something saying that band and position there's really no way. If I know band, I don't know position. If I know position, I don't know band. It's almost like an uncertainty principle. So it's when we're talking about topology, we're basically making sure that we're making a statement about how position and band are really not possible to know at the same time. And this really has lots of consequences. And now I want to tell you something new, which is kind of like a very simple consequence of this that has quite a bit of consequences, including the low boundary correspondence. And how am I doing with time?
About 10 more minutes.
Okay, so let's do it. So if I'm telling you, if I know the band, I cannot construct a position like a state with a well-defined position. And if I construct a state of a well-defined position, I cannot know which band it came from. What if I do it anyway, right? What if I force it? Imagine that I force it by putting a local potential, by putting an impurity operator that has some strength B, and it's localized. It has an eigenstate phi I, which is perfectly localized on one spot. Okay, this is just so my Hamiltonian. It's going to be perturbed by this potential. So what usually happens when I have a band, any kind of band, and I'm putting it like a sling band because it's a cookie that anyway, it doesn't really matter. When I put an impurity potential, usually I create a state on the band edge, right? We all kind of know this. So basically, I create a bond state out of my band continuum. And if I make the potential stronger and stronger, what would generally happen is that this state, so if I draw here an energy axis, this state will become more and more energetic, and eventually I'll completely take it away from the band, right? And when I completely take it away from the band, the energy of this state is basically going to be V. It's going to be an eigenstate of V itself. And what is going to be the wave function of this state is just this. So I construct it. I have a band, which has a band dictated by P alpha, okay? And I constructed a state, which is phi V at very, very high energies by putting simply a perturbation, which is this local potential. Well, how do I usually calculate this bound state out of the band? With perturbation theory, I have to sum the Dyson equation, and I'm not going to extend very much into it. I'm just going to write you the form of the eigenstate that I could write. So this is the form of the bound state due to this perturbation. Perturbation of potential V and with an eigenstate phi. What this is here, that I'm basically hiding it in terms of writing it in terms of the projector and E over E alpha, this is just the local Green's function. But if we're assuming this to be basically a flat band, all of the energies are basically the same. So I have here, what I have here is the projector times this local state. Well, that is your local state that we know that we cannot make it infinitely sharp. Right? This is exactly the expression that I had from the state that I tried to construct, and I cannot make it infinitely sharp. So really, what goes wrong, right? Basically what I am saying is that if I were to construct a localized state out of a this band, if I'm going to calculate the wave functions of bound states on a topological band due to some impurity potential, I am going to get at most something that is localized with like the same type of localization constraints as the value functions. Or basically there's minimum spread for this state. It's not quite the same localization strength as the localization as the value function. So really what happens is, well, we have a problem here. And the only way, as P goes, so here as P goes to infinity, the energy of the state, which is around P, this would be 1, and that would be exactly the state that I get. So it's a problem because it's a topological band, and the only way that I could solve this is by considering, like they're saying that this P is large enough that would not only see this band, but would see other bands that all together would make a trivial band, right? So I don't have only this one. I will have another band. Let's say P alpha equals 1, P alpha equals 2. Both of them are topological. But all of them together, they're actually trivial. So then, if I write out my bound states wave function, at the limits of being V very large and the energy of that state being very large, I have P1 plus P2. And now this state exists in this projector because both of them are trivial. So this state exists in this space and there's no problem, and I will actually have a solution which will be the eigenstate of B. So I would have a completely happy state. I would be able to construct the happy state here at very large energies if I would take it together from two bands, which together would be trivial. So if I construct this state, I was not able to take it from here. I was not able to take it from here, but I'm happy taking it from both sides. Okay, but so then let's imagine the path to get there. How did I manage to get there? Okay, I needed to start coming, like let's say B is very, very small. It starts coming from somewhere, but it comes from which one? It comes from here or comes from here? Better come from both, because otherwise you would have a problem. So it comes from both. And as I make dB larger, this guy will go all the way to infinity, and this guy will just stop somewhere. So in order to construct this state, I could do it very happily by taking one state from here and one state from here. But in the end of the day, I need all my numbers to match up. So there's an additional state that is required to stay within the side of the gap. And I didn't tell you that this is an edge. I didn't tell you what is the topology of the assumption of the topology. I just told you that by the fact that I cannot construct the eigenstate of the perturbation of the potential of that I put of my perturbation, I was required to construct a state inside of the gap between the two topological bands. So that's a very kind of generic notion, right?
How do you argue that it has to be within the gap? Like maybe you can enter P alpha equals to 2 or even slightly above it, or depending on how large P is.
If why doesn't it enter?
Yeah, or even maybe go a little bit above.
Okay, so so let's try to do it. It goes back to the structure of the Green's function, and actually you can even forget about the Green's function. It goes to the structure of the overlap between the topological band and the trivial band generated by the impurity. So let's say, let me call it V. This is basically this. So let me write again. All of the bound states are going to have the exact same structure. Okay, so that's going to be written in this form. In this space of V, P1, E minus E1 plus P2, E minus E2, acting on this state V. So before we said that the energy of the state was very, very large. So this E1, E2 didn't matter. And we just had B over E, which was about 1. And therefore, we have this state at very high energies. Now we want to see that it's possible to have a state that is with E between E1 and E2. Okay, that's good. That's what we want to see. So how is it possible to even satisfy this equation in a way that for V equals infinity, I would be able to have a state at finite energy? So that's very, very, very strange. Basically, this state at finite energy is a state of finite energy for infinitely large V. Okay? So it really, if you think about H plus V as your full perturbed Hamiltonian, this is a state that comes for H, not from V. Okay? V is infinity. Okay, so how can I have a solution for this? I have to have a 0 here. Okay. And yeah, so we can write this explicitly. Okay, so yeah, we will have a 0. It's in fact going to be required. But let's say that basically P1 is going to be the sum over all of the wave functions in the first band, right? So if I put it here, you would see so that P1 times phi, this phi here, it would actually be sum over n, psi n1, psi n1. And I'm going to now transform this state into momentum space. Okay, so this is a local state. I can write it as a linear combination of block states, which I'm going to call phi v, and that needs to be at the same moment. There's going to be a delta. This could be m here, and then there's a delta function that will relate kn and km. So if I rewrite, I get v sum over n, the overlap in n of the band 1 with v, energy minus 1. We again said that every state in the band is at the same energy to simplify. And the overlap of the two, the second band. Now, I told you that whenever I have a Vanier obstruction, I will have a zero. I will have this operator is going to be singular, and there's going to be zero here. So there's one pole that is just going to have vanishing weight. There's necessarily a state, the projection with this guy, there's necessarily going to be one pole that leaves all this energy. So if I'm going to, I'll draw this function for you, okay? I'll draw this function for you in energy. I have the first band is here. I have a bunch of poles labeled by n. One of them is going to be missing. At least one of them is going to be missing. And it's going to be staying here on band 2. So now this is something that is going to decay with energy. Like that. And you're necessarily going to have a zero. So it's a consequence of the zero on the weight of this pole that you need to have a zero in the gap between this and this line. That is the argument. So these guys always exist as long as you have an obstruction to reach these particular atomic limits. And in a topological band, any atomic limit is impossible to get. So basically, every single topological band, it will have an in-gap state for whatever is the local potential that you create, as long as it's strong enough. So there's a kind of a way of thinking about this state in one very specific scenario, which is the Chern number or the Chern insulator, which is, imagine that you have Chern insulator, you make it a big hole, huge hole. You expect to have an edge mode going around inside of that hole, right? It has a momentum because it's like continuous. And as you make the hole smaller and smaller and smaller, you start quantizing their states. And eventually they kind of start disappearing. But what I am saying is that once you make that hole really, really small, there's at least going to be like one state left. And in fact, that's also going to be true no matter really the topological states. No matter if it's fragile, no matter if it's strong, no matter anything. So it's a direct consequence of the Vanier obstruction that if you have a strong enough local potential, you're going to bind the state. Now that state does not need to be at zero or exactly at zero energy or something like that. It can be somewhere, but it will be between the two topological bands. Okay, that state is something that call it a ring state. The reason I call it a ring state is that it exists at a finite energy for infinitely large V. The only way to do that is by suppressing its weight right at the core where the impurity is. Okay, so the profile, so if I look at the spatial profile of this state, if I put an impurity like local potential, it needs to be something like that, right? It needs to be exactly zero, exactly where the impurity is, because the impurity is arbitrarily large, so it gets to infinity, and then it's going to decay exponentially, just like any other impact state. Because it's anytime you have, so you have a spectrum, right? And then you have a state. You don't know where that state is. And now I feel like that. But you have a state somewhere here, so it's going to decay exponentially, but it's going to have two different behavior, right? There's a core and there's a tail. And the tail is going to decay exponentially, but if the core, then it needs to change and it needs to start suppressing itself right in the middle. So that is completely general in terms of what is the different topology. And yeah, so another thing, so these types of states, the fact that it's generally this is relative, this is something that I'm telling you now, but the existence of these zeros of the Green's function has been noticed before for Chern insulators. In that paper, which is a paper by Robert T. and Ziegler, it's actually quite nice because one thing that they do is that they describe how the edge modes themselves are a bunch of, like, you can think of these states as extending in one dimension. So this is kind of like the minimal type of both boundary correspondence, and the edge is basically what we call codimension one defect. That's basically brings in the edge. And with that, I would like to, yeah, thank you so much.
Okay, we have time for a few questions.
Thank you for a very interesting talk. I'd like to ask a question about the diagram just raised.
Oh, sorry.
okay, I think we remember that.
I'll draw it again. It's very
No, that's very fine. Yeah, but that crossing at zero, doesn't that rely on having the S1 and S2 be both positive or have the same sign?
So S is always going to be positive because it's basically it's the diagonal entries of a positive and definite.
Oh.
So S was just the projector times P. This is positive semi-definite. I can decompose it as something like this. And also we know that the total is, in the end of the day, you know, the total weight, this is basically going to tell you about the weight. Let's put it this way. Let's say that this is like S character, okay? And this is your topological value. So S and N of the beta is basically telling you how much S-like is a specific block state of your band. Okay, in total, it needs to sum up to one. You know, the weight of that is distributed between this band and this band in total is going to be sum up to one. But what I am saying is that just because of the topological character, there's going to be at least one state which is completely orthogonal to S. It has no S at all, right? And that's so there's going to be one state in the other band which is completely S. And then that is enough to require this zero.
And can I ask a quick separate question? So this way of probing the presence of topological bands by putting in a strong impurity and seeing there's a heat gap state, can I view it as a because when we talk about topological basis, of course, we can talk about boundary correspondence. In many cases, there are gapless boundary modes, and that helps to detect the presence of logical base. Here, you're kind of probing this logical base, not using boundary correspondence. You're really going into bulk and putting in an impurity and seeing.
Right. So, but it's of course hard to do it because there's no free large base, right? So first of all, you don't know what which energy it is. So you may need to swipe a bit of energies. But one thing that you can say is that no matter the impurity, you'll have a bond state. So if you're a experimentalist and you're material and you have SPN and you have like this vacancy and that vacancy, and all of these vacancies are showing you something, at least it gives you a very good idea that you are in the presence of something topological. And then you're welcome to go to the edge and see if something is there. But there's also some problems with when we think about low boundary correspondence in general, particularly in phases which are protected by some crystalline symmetry, is that the boundaries themselves break the symmetry, right? So by construction here, I'm thinking about an impurity that does not break the symmetry. So you should have a mode, right? So even if you don't have an edge.
So magnetic impurity, for example, doesn't work.
Depends on which phase you are considering, right? So if I'm saying that if you have an obstruction to get to the eigenstate of the impurity, you will have it.
But if I have a single magnetic impurity, then there is some strong correlation physics comes into, right? Because it could be a condo.
Right, okay. Yeah, so this is a fully single particle feature that I'm talking about. Then in these cases, you have an impurity that has like a free spin in there, and then there's all kinds of correlation effects that could show up. And it's very much possible that you construct this state. Imagine in a normal topological insulator with a hole, you construct a state like that, and you have spin rotation symmetry, and you just create a free spin there, and then you can talk about the physics of that. What is interesting is that it's going to force you to be on a specific low energy, right? This state is forced to be within the energy bandwidth of your combined states, of your combined bands that would lead trivial altogether. So, so it's not, you don't need to fine tune, right? It becomes the energy of this state is very, very insensitive to the impurity potential itself. So that can be maybe useful, but you know, but then that would be physics somehow.
Hi, so you mentioned the Dyson series, and it looked like you were taking the first term in that series, which I guess is justified as v goes to infinity. If I look at small finite v, does this analysis break down at some point?
It does not. So the Dyson series, you can sum it exactly. Right? So when you sum it exactly, so
so your E2 is a self energy.
Right,
Okay.
right. So you basically have something like G0 plus G01 minus V1 minus VG. That would be the total sum. So these additional states, they will come from poles that we can here. Right? So this would be your original band unperturbed states are going to be poles of the unperturbed Green function. And the perturbation will give you additional poles, which are these. And then you can see that when VG equals 1, so for V equals infinity, when G has a 0, you have a pole here. So that is actually from the total sum of the
Any more questions in the room? Should we go to those? Other questions online? Oh, okay. I think you have answered all of our questions. Then let's give a big hand for Raquel.